Suppose we set up an electrochemical cell with a zinc electrode in a 1 molar zinc sulfate solution and a copper electrode in a 1 molar copper 2 sulfate solution. There's our bar of zinc, there's our bar of copper. We're going to connect these two. We're going to put in a salt bridge. Incidentally, the sulfate ions and whatever's in the salt bridge are called counter ions. They help maintain the electrical neutrality of the system, but they don't participate in the reaction. We observe that current flows spontaneously, that zinc is the anode, and copper the cathode. We notice that we have current flowing. We notice that zinc is the anode because it's being eaten away. And we notice that copper is plating out onto the copper cathode. We set this up. It went on its own. So this is a galvanic cell with electrons going from the zinc to the copper. We also find that if we connect a voltmeter to the electrodes, it reads a potential of 1.10 volts. If I put a voltmeter in here, which because a voltmeter has a very high resistance, basically all flow of electricity will stop, but it reads 1.10 volts. It's reasonable to surmise that the 1.10 volt value is due partially to what's happening to the zinc, oxidation, and partially to what's happening to the copper, reduction. In other words, 1.10 volts is the zinc-copper combination, but what is the zinc, or copper, alone? And the answer is, we can't know that, because we can't get the zinc or copper by itself. We always have to compare it to something. The zinc is a half cell. The copper is a half cell. In order to have an electrochemical setup, you have to have two half cells. That's why we need the standard hydrogen electrode, which we're going to draw here on the right side of the screen. In the standard hydrogen electrode, we have a glass tube that's open on the top, it's open on the bottom, and then there's an arm off to the side. In the top we have, say, a rubber stopper that has a wire inserted through it and a platinum electrode at the bottom. We have a 1 molar hydrochloric acid solution, and then through the side arm of this tube we are maintaining an input of hydrogen gas at 1 atmosphere of pressure. That is the standard hydrogen electrode. By international agreement, the potential for the standard hydrogen electrode by itself is 0.00 volts. The standard hydrogen electrode is thus the comparison standard for all else. And what we're going to do next is hook up our zinc half cell with the standard hydrogen electrode. Then we're going to hook up our copper half cell with the standard hydrogen electrode and see what kind of results we get. So let's hook up our zinc half cell to the standard hydrogen electrode. We make the zinc ion concentration in the solution 1 molar, just like the 1 molar hydrogen ion concentration in the other half cell. So at the bottom of the screen you can see we're going to make the zinc sulfate concentration 1 molar. We observe zinc being oxidized to zinc ion. We note that the zinc is being eaten away. In our diagram here, that's what we have happening with the zinc. Zinc metal is being oxidized to zinc ion, and in order for that to happen, we're going to kick electrons away from the zinc. In this case, the electrons will be traveling to the right towards the standard hydrogen electrode. And on that side, we notice that H+ is being reduced to hydrogen gas because we notice bubbles being formed. In the lower right portion of the screen, we're going to show some bubbles being formed. When we hook the voltmeter up to this, the voltmeter reads 0.76 volts for zinc being oxidized. What about copper? Now we hook up our copper half cell to the standard hydrogen electrode. Again, we make the copper 2 ion concentration in the solution 1 molar. So we'll do that now at the bottom of the screen. We observe that copper 2 plus ions are being reduced on the copper electrode. What we have happening is copper 2 ions that are coming out of solution and plating out onto the copper electrode, and that is a reduction. Therefore, the copper must be the cathode. The hydrogen gas must be being oxidized because we notice that the pH in the standard hydrogen electrode cell is dropping. In other words, we're continually feeding hydrogen in through this side arm, and it is being oxidized to form more H+. And when we have more H+, the pH is going to be dropping. When we hook the voltmeter up to this case, the voltmeter reads 0.34 volts for copper 2 being reduced. What does all this mean? Voltmeter readings for half cells paired up with a standard hydrogen electrode are standard potentials. That's what the S stands for in standard hydrogen electrode. And we symbolize that E0. And here, standard means three things. Any solution concentration being 1 molar, the pressure of any gas participating in the reaction equaling 1.00 atmospheres, and the temperature being 25 degrees Celsius. In our measurements, this is what we found. We found for the oxidation of zinc that the cell potential was 0.76 volts, and for copper 2 being reduced, we got 0.34 volts. Now, by convention, all standard potentials are written as reductions. What we had in our reaction was zinc being oxidized. I've rewritten it as a reduction, and when we do that, we need to change the sign of the standard potential. Now, copper 2 was already a reduction, so the value that we measured does not change sign. It's going to be simply positive 0.34 volts. And way back when we started this, when we hooked up a zinc half cell with a copper 2 half cell, you might remember that we measured the potential to be 1.10 volts, and that is how far apart those two numbers are right there, 1.10 volts. All half cell reactions have been tested relative to a standard hydrogen electrode and their standard reduction potentials tabulated. That's the importance of a standard hydrogen electrode.